Hello everyone, welcome to lecture 20 of the online course on Introduction to Microwave and Optical Metamaterials. In this lecture, it will be a continuation of the effective medium theory. Here we will complete the derivations of the Maxwell-Garnett theory, and we will also discuss the Bregman effective medium theory and Nicolson-Ross-Weir method. So here will be the lecture outline. As I mentioned, we will complete this derivation. We will look into the equations for Bregman effective medium theory. We will discuss the limitations of the Maxwell-Garnett theory. We will introduce another interesting method of Nicolson-Ross-Weir, and we will see the application areas where you can use this method and what are the limitations associated. So, to continue from the previous lecture, we have seen that if the material is excited by an external electric field, within the quasi-static approximation, you can say that such field can be considered as constant over the length scale of each sphere. That means that is possible when the sphere is much sub-wavelength. That means the wavelength of the light is much larger than the dimension of the sphere. So, you can consider it to be the field to be quasi-static. So, in that case, what will happen? The average operator could integrate over a sufficiently large volume in order to provide a accurate description of the average fields in the original medium. So, you can write the average displacement field to be equal to epsilon naught epsilon mg and then the average electric field. So, what is this? You have already seen that this is the scenario where you can apply Maxwell-Garnett approximation, that you have some inclusions which are again sub-wavelength in size. They are put within this host medium which has got a permittivity of epsilon h. So, the permittivity of the inclusions are given as epsilon I. You can assume them to be sub-wavelength spheres, and then finally you can obtain a effective medium which has got a permittivity of epsilon mg. Now, this equation can also be written as epsilon naught epsilon h e plus p. So, you can actually separate out the polarization. So, you can write down the contribution of the electric field in the host medium plus the polarization that is coming because of the inclusions, right. So, this is how you can use epsilon mg, that will give you the effective relative permittivity that can model the actual mixture. Now, a couple of important things here, that the average dipole response, which is this average capital P, is nothing but n times small p, right. Here small p is typically not equal to ph, that is the host dipole moment. It has to be now calculated in the presence of all other dipoles. That means the evaluation of this dipole moment can be classically performed by evaluating the local electric field EL. That means this is basically the field which is felt by each individual dipole in the presence of all other dipoles, right. So, this field is basically the average field, this average E augmented by a contribution due to the average polarization that basically surrounds each dipole, and that is also known as Lorentz field. Now, to find this particular local electric field which is acting on a single dipole, a simple model of the mixture can be adopted. So, let us assume this particular scenario where a fictitious spherical boundary separates the macroscopic background with average polarization P from a microscopic spherical cavity here, that is surrounding the dipole at the center of the sphere. So, this is the dipole and this is the sphere that is within this particular microscopic cavity that lies within this macroscopic background. Now, what is the role of this one? So, a microscopic spherical cavity here can separate the homogeneous background from a microscopic phase, in which the dipole is basically included. So, because of this dipole, that is a the electric field will be, the charge separation will be like this, and this is the field. Okay. Now, the field at the dipole location, which is at the center of the sphere, is basically the local electric field EL. Now, how you can write this EL? Okay, you can write this as the average field, okay, plus the average polarization divided by 3 epsilon naught epsilon h. And you can also write that the dipole moment small p will be equal to, that is proportional to the electric field with the polarizability alpha. So, you can write it as epsilon naught epsilon h alpha and the average electric field plus alpha average polarization divided by 3. Okay. Now, we can now retrieve this Maxwell-Garnett permittivity, which is our effective permittivity, in terms of this polarizability alpha and then n, which is basically the number density, which tells you how many such dipoles are there in a particular volume. So, you can write epsilon mg equals epsilon h 1 plus n alpha divided by 1 minus n alpha by 3. Now, in the case of a very diluted media, you can consider this term to be equal to 1. Okay. So, in that kind of approximation, the effective permittivity epsilon mg will simply look like epsilon h 1 plus n alpha, right. And the same expression can easily be obtained when you consider your EL to be equal to the average electric field. Now, this particular approximation will happen in a very diluted medium, means there are very less number of inclusions in the host medium, okay. And this is possible because the interaction between the dipoles are weak. So, your local electric field is nothing but the average electric field, right. So, with this you can also write that n alpha by 3 will be equal to epsilon mg minus h divided by epsilon mg plus 2 epsilon h, right. So, this particular relation is also called the Clausius-Missoti formula or Maxwell's formula or the Lorentz-Lauren formula. Okay. So, in this particular equation, if you substitute the value of the polarizability alpha that is coming from the quasi-static theory. So, you can find out the polarizability as 3V, V is basically the volume of the sphere, epsilon I minus epsilon h divided by epsilon I plus 2 epsilon h. So, in that case the Clausius-Missoti relation looks like this. So, you have 3V, okay, epsilon I minus epsilon h divided by epsilon I plus 2 epsilon h, n by 3 equals epsilon mg minus epsilon h divided by epsilon mg plus 2 epsilon h. So, from this you can actually see that there is n and v, okay. If you basically multiply this, you are getting f, which is basically the volume fraction, okay, of the inclusions. So, here these are spheres in the host medium. So, you can simplify this expression. So, n v can be written as okay, or you can say, so this side, so n v will be written as f, okay, that is the volume fraction. So, this particular equation is also known as the Rayleigh formula that relates the effective permittivity of the of this effective medium epsilon mg to the constituents permittivity, which is basically epsilon I and epsilon h, okay, for the parameter which is known as volume fraction f, that is calculated as nv. So, v is the volume, n is the number, right. So, this basically gives you the volume fraction of the inclusions in a particular medium. So, if you try to solve this and try to find out what will be the absolute value of epsilon mg, okay, so that you can obtain from this equation, and you can write it as epsilon mg equals epsilon h 1 plus 3 f epsilon I minus epsilon h divided by this fraction, okay. So, this denominator will be simply like epsilon I plus 2 epsilon h minus f epsilon I minus epsilon h. So, this is how, using the value of epsilon I, epsilon h and f, you can calculate what is the effective permittivity of the medium. So, this is one very important formula. So, this is called the Maxwell-Garnett formula, okay, and This simple formula represents the classical approach of homogenizing composite media, and it is widely used in many applications. Okay. Now, it is interesting to notice that the only parameters for retrieving this Maxwell-Garnett permittivity are nothing but the individual permittivity of the inclusions and the host, and also you need to know the volume fraction. That means in the host how much volume is actually occupied by the inclusions. Okay. Once you know that, you can use this formula and find out what will be the effective permittivity of this composite medium. Now, there are a couple of interesting observations that this formula does not require the spheres to be of the same size, and they do not need to be located at a specific position or location. Okay. So, you do not need to make a periodic array or something like that, there is no such requirement. The only requirement is that the spheres should be sub-wavelength. That means, the wavelength in the medium should be much larger than the size of these inclusions. Okay. So, you can also see that Maxwell-Garnett theory predicts that when the volume fraction goes to 0, the effective medium will be same as the host medium. When the volume fraction goes to 1, then the effective permittivity will be same as that of the inclusion permittivity epsilon I. Makes sense, right? So, till now we have seen that the Maxwell-Garnett formula represents a valid homogenization model for mixtures with well defined host medium and inclusions. But there are some cases, okay, where things get mixed up. Okay, we will see those. Now, Maxwell-Garnett results are very accurate for relatively small values of the inclusion volume factor f. Okay. Now, for aggregate mixtures with random distributions of 2 or more constituents, you will see that the effective medium theory which are based on statistical formulation becomes more suitable, something like this. Okay. So, here this is the case of a inhomogeneous mixture. Okay. So, any region in the mixture can be either this material or the other. Okay. So, you can always model this as effective medium, which is epsilon Br. Okay. So, what you can see that there are two phase inhomogeneous material, okay, and a space filling random mixture has happened between the two phases. So, it is clearly marked here that one phase will have dielectric constant of epsilon I, and if you consider that to have a filling fraction of f, then the other phase which has got dielectric constant of epsilon h will have a volume fraction of 1 minus f. Okay. So, on the right here you can see this is the Brugman theory model of this structure. So, it has got a background medium of effective permittivity epsilon Br that is hosting very small spheres, okay, whose dielectric constant is epsilon I with probability f, or they can be epsilon h with probability 1 minus f. So, you can consider a two phase microstructure of the type that is shown here, where the constituent with permittivity epsilon I has a volume fraction of f, and the constituents with permittivity epsilon h will have a volume fraction of 1 minus f. So, you can now model this mixture as a continuous medium hosting a distribution of small spherical inclusions of the two different type of dielectric permittivities epsilon I and epsilon h, okay, and the probability of finding spheres with permittivity epsilon I will be f. So, the probability of finding spheres with permittivity epsilon h will be 1 minus f. Okay. So, this is how where things vary from the previous case to this Brugman case. So, let us assume that the host medium of the Brugman mixture has unknown effective permittivity, which is epsilon Br, okay, that we are supposed to find out, and that will give you the transparency or invisibility condition for the distribution of the spherical inclusions, right. So, if you consider the distribution of spheres, okay, can be it can be, the permittivity can be epsilon I with probability f or epsilon h with probability 1 minus f. Okay. So, you can find out an average transparency condition that will have this equation. Okay. So, it says f epsilon I minus epsilon br divided by epsilon I plus 2 epsilon br plus 1 minus f epsilon h minus epsilon br divided by this will be equal to 0. So, this one is known as the Brugmann theory. Okay. So, you can also do the maths and find out what will be epsilon br from this particular equation. Now, if the formula for spherical inclusions, now in case you have multi-phase aggregates, not only two phase, so you have more number of elements mixing up together. So, you can also extend this formula to this kind of multi-phase aggregate, and there you will write that summation small m equals 1 to capital M f m epsilon h minus epsilon br divided by, okay, this will be epsilon m basically. Okay. So, that will tell you the fill factor. Okay. So, I think this is the correct equation. So, you will see that epsilon summation over small m starting from 1 to capital M. So, there are total m number of phases materials present. Okay. So, the probability of finding each phase will be f m, the permittivity is epsilon m minus epsilon br divided by epsilon h plus 2 epsilon br, that should add up to 0, right. So, as you can, as I have already told, that f m is basically the fill factor of the mth constituent of the mixture, and capital M is the total number of phases, right. So, this tells you the effective permittivity that you can get from the Brugmann theory. Okay. Now, let us look into some important limitations of Maxwell-Garnett theory and the other one. Okay. So, the first thing that is to be mentioned here is that the particles with very small depolarization factor. Okay. So, when you have a low depolarization factor, that basically implies a elongated shape of the particle, and that will result in a stronger particle-particle interaction. Okay. Now, this is what you do not want, you actually do not want your epsilon L, sorry EL, the local electric field, to be very different from the average electric field, right. So, in such a scenario, which is similar to the case of a mixture of large inclusions fill factor, you can go for the Brugmann prediction, right. So, whenever this Maxwell theory will not be sufficient, you can go for the Brugmann method. Another scenario in which the Brugmann theory provides a more realistic electromagnetic description is when there are mixtures with large differences in the permittivity of the constituents, something like metal dielectric mixtures, where you will see that a percolation phenomena above a threshold of the metallic phase takes place or happens. So, this is basically, percolation is nothing but movement and filtering of fluids through a porous medium. So, these are the two cases where you will see that Brugmann theory produces a much more closer response as compared to Maxwell-Garnett theory. Now, this threshold in the critical metal filling factor, okay, above which the formation of long range connectivity between the metallic grains or the optical response of the mixture can change abruptly. So, there is a limit between which this kind of theory will be valid, right. So, now let us look into another method called Nicolson-Ross-Weir method. So, this is a homogenization method based on the inversion of the Fresnel formula relative to the transmission and reflection coefficients through slabs of homogeneous media. So, this technique was conceived to estimate the average, or you can say the complex permittivity and permeability of an unknown material from the measured transmittance and reflectance over a spectrum, okay, for a finite thickness sample. So, I will show you with some examples. Okay. So, it was originally proposed in the time domain for pulsed measurement systems, and then later it was adapted to higher resolution and then to frequency domain systems. The transmission and the reflection spectra may be retrieved with experiments or from numerical simulations. So, here is how it looks like. So, let us assume a slab of thickness d, which is made of some unknown natural or artificial mixtures. This can be modeled as a slab of homogeneous medium, which has got effective permittivity and permeability, epsilon effective and epsilon mu effective. Okay. So, here you can see that it is the actual medium is basically a composite medium, okay, and then there is a wave that is falling on this medium and you have got the reflectance and the transmittance, right. Now, you are basically mapping these properties of transmittance and reflectance and trying to guess what would be the effective permittivity and permeability, which could have given you that kind of reflectance and transmittance. So, first thing that we assume that the thickness of this slab will also be d, okay, and the complex reflection and transmission coefficients that you have got capital R and capital T under normal incidence plane wave. Okay, if you know this, you can either you can know this by experiment or by numerical simulation, and once you know, you can actually correlate them to the Fresnel reflection and the transmission coefficient with this. So, here you can see this equation has got two new terms, one is n effective, okay, and then you have gamma, right. So, what are these two things? N effective is basically coming from the effective refractive index of the slab, which you can calculate as square root of mu effective and epsilon effective. Then you have the free space wave number that is appearing here, k, that is omega by c, and then you have gamma, which is basically the reflection coefficient across the first interface between the input medium, and if you assume that this particular slab is a semi infinite one, which has got permittivity epsilon effective and mu effective, right. So, what will be the reflection coefficient from this interface? So, that actually gives you this. Now, if you look at only normal incidence, you can write gamma equals eta effective minus eta naught divided by eta effective plus eta naught. Now, what is eta effective? That is coming from square root of mu effective epsilon effective, and this is nothing but the effective intrinsic impedance of the homogeneous slab. Eta naught, obviously it is the intrinsic impedance of the input or the output medium. You can consider this as vacuum impedance as well, right. Now, the inversion of the equations of R and T will lead to this, that you can now calculate eta effective from eta naught, and when you have the values of R and T given, you can find out what is your effective intrinsic impedance of this homogeneous slab. And once you know this, you can calculate the expression for this quantity q, that will be given as e to the power minus I k n effective into d. So, q can be written in terms of T, R and n effective in this particular form. So, T divided by 1 minus R n effective minus eta naught divided by eta effective. So, it is not n, this is eta effective, this is the intrinsic impedance, right. So, this is the effective impedance of the slab and this is the intrinsic impedance of the input of the output medium. So, once you know the value of eta effective and q, you can write down n effective as I k d log q, and you can expand this as 1 by k d I log of modulus q minus argument of q plus 2 m pi. Okay. Now, here you will see that the log q is the complex multi-valued logarithm of this quantity q. This is basically the ordinary real logarithm of the modulus of q. Argument is basically giving you the principal branch, that is when m equals 0, and then m can give you the other integer branches as well. So, you can also have plus minus 1, plus minus 2, which are basically indicating the branch of log q. So, once you know this n effective, you can effective parameters can be written as epsilon effective will be k n effective divided by omega eta effective, and you can write effective permeability mu effective to be equal to K n effective eta effective divided by omega. Okay. So, that way from reflection and transmission coefficient you can find out what is the effective permittivity of this material. So, here you will be able to find out what is the effective permittivity as well as effective permeability of the material. Now, there are some limitations to this factor as well. So, you will see that while the choice of sign for the effective impedance and the refractive index does not alter the value of the effective parameters which are extracted via these equations. Okay. So, there is an intrinsic ambiguity in the definition of this equation, which is nothing but real of n effective. So, it is coming from this equation, okay, and that is mainly coming from the fact that the multi-valued complex algorithm log q, okay, and it also depends on the choice of the branch order m. Okay. And this problem may be solved in very thin slabs in which the effective wavelength is much larger than 2D. Okay. So, this particular method, Nicolson-Ross-Weir method, can also be extended to the characterization of mixtures in the case of oblique plane wave incidence. Here we have just shown it for the normal incidence. So, that can be used for study of spatial dispersion effects in metamaterials, right. So, the application of homogenization principle constitute for bulk natural and artificial mixtures may be misleading for the homogenization of very thin films. For structured films or artificial surfaces, usually more sophisticated techniques have been developed based on the interaction of non-local effective surface susceptibility and all those. So, we will not cover and go into those details, we will basically look into the normally or regularly used effective medium theory approaches, which are going to be very useful for defining the properties when you will be going further and designing the metamaterials. So, with that we will conclude this, and if you have got any query regarding this lecture, drop an email to this email address mentioning the lecture number and the course title on the subject line. Thank you.